I want to announce our first speaker. So the first speaker is Ness from the group of Yoav Sagi from the physics department, and he's talking to us about something very interesting. So he talks about a speed limit that quantum dynamics has, and they saw this in the experiments. So revealing the quantum speed limits crossover. All right, Gal, please go ahead.
Thank you, Michael, for this introduction. So hey all, my name is Ness, and I will briefly tell you about this recently published observation of us. So the question that we ask here is how fast can a quantum system evolve in time? And of course, this is a very fundamental question that has implications in quantum computation, simulation, and sensing. And the paradigm which we use to answer this question is called quantum speed limits. So what are these limits anyway? We all know that Heisenberg uncertainty principle regarding simultaneous measurement of momentum and position, which is conventionally cast to delta E delta t. But time is not a proper quantum operator. So what's the meaning of delta t? In order to rigorously answer this riddle, Mansam and Tam proposed the following interpretation. They used this tau mt and related the energy uncertainty to the minimal time it takes to evolve from an initial state to an orthogonal final state. So this is the minimal evolution time, and if you want to generalize it to any two states, and we here consider unitary dynamics of constant Hamiltonians, and if you want to generalize it to any two states, then you can consider the two-time state overlap. This is the overlap of the time evolved state with the initial state we begin with, and you know it will start from 1, and it should end somewhere around h bar over delta E, and we can naively take a linear line, but we know from short times expansion that we more likely to have a parabola here, because this is basically the Zeno effect, right? And so one may ask, can we go faster than this parabola, or maybe we must go slower? And this is exactly what the Mansam-Tam limit tells us, that we must go slower than this parabola. In fact, we have this cosine law. And the meaning of limit is that we have all this pink regime, which is forbidden by the Mansam-Tam bound. So any quantum evolution would be slower than that, and the two-time state overlap would be higher than this forbidden regime. Now, if you ask what systems saturate, yes, Yossi?
I don't know why it's a parabola. Why isn't it a trigonometric function?
So this is a cosine. This is a parabola.
I see, okay.
This is like, in fact, and this cosine is the exact cosine that we have in Rabi oscillations. Rabi oscillation of balanced qubit is the system that saturates this bound. But in realistic applications, we are interested in multi-level system, because even if we consider a qubit system, we need more levels in order to read it out. So the question is therefore, how can we study these limits in a multi-level system? And in multi-level system, the limits are more rich. So we also have another bound named after Margalus and Levitin, and they found out that the minimal time for orthogonalization is not only bounded by the energy uncertainty, but also by the energy itself, above the ground state energy, with some different functionality. So we have another forbidden region here in yellow. And so our goal is to study these bounds experimentally. So in order to probe these limits, what you need to have is a measure of the energy uncertainty, the energy itself, and of course the two-time state overlap, which is difficult because usually as experimentalists we don't have time machines. So observables that regarding two times are more difficult to measure. And now let's see how we use matter wave interferometry in order to probe these observables. So former experiments in this direction of quantum speed limits were done, but they were unfortunately limited to qubit or effective qubit Hamiltonians, and they only studied the Margalus-Levitin bound of the Mansam-Tam bound of the energy uncertainty. So there are therefore few novel points in our work. First is that we probe the limits on a multi-level system, and we, by observing both limits, we reveal a crossover between the two bounds, which we'll shortly see. And to do that, we have developed an interferometry technique for matter wave interferometry that leverage a very unique experimental tool called spin-dependent optical lattice. Now, but what I mean by speed-dependent optical lattice is that we have some potential landscape that can individually address the two internal spin states of an atom, of the single cesium atom that we work with. So imagine that we pump our atom to the blue down state. We have another potential which the atom does not experience, which is the red one of the upper part of the wave function, which we can move as we wish because the atom wouldn't know. And let's say we move it for some displacement delta x. Now we can shine a pi half pulse, which will create an equal superposition of both spins. The red part of the wave function is excited, so it will evolve in time. So we have this evolving part, while the down part is stationary, and it will serve as a reference for the initial state. And therefore, when we shine a second pi half pulse and measure the population of the down state, we will get this kind of Ramsey fringe as a function of the phase between the two pulses. We get a Ramsey fringe which basically tells us all that we need to know about the system. So from the visibility of this fringe, we directly get the two time state overlap, and also from its time expansion, we get the energy uncertainty. Also from the visibility, from the phase of this fringe, we get the mean energy. So we have these three quantities that we wish to have, and now we can explore the limits with them. So this is how it looks like. Here we plot the visibility or the two-time state overlap as a function of evolution time, and we see it reduces. And because we have the two measures, we can also plot the two bounds, the Mandelstam bound due to the energy uncertainty and the Margalus-Levitin bound due to the energetic value itself above the ground state energy. And already from this example, we can get two conclusions. So first is that the overlap respects both limits. We see that the blue measured data points are above the two forbidden regions. And second is that there is a certain time, marked here by tau c, where the two limits cross. At the beginning, we have a Mandelstam limit that restricts the evolution, and then we cross over to the Margalus-Levitin bound due to the energy. Now, this specific experiment was done with some excitation due to a lattice shift between the excited and ground lattice of 4% lattice height. We can increase this excitation to 8%, and we see that the crossing time shifts a bit further. And if we increase even more the excitation, we see that there is no crossing at all. So already from this scan of how we open the lattice, we see two types of dynamics. In one type, there is a crossover at some certain time, tau c, and in the second one, there is no crossover. So we want to have some outlook on that. So we plot here all the points, and we plot that we measured, and we plot their energy uncertainty versus mean energy. Okay, all these blue points, and if we want to talk in language of speed limits, so we call this the reciprocal Mandelstam orthogonalization time versus the Margalus-Levitin orthogonalization time. And all these points were initialized in the ground state of the optical lattice. We can also initialize points in the first and second excited states or Fock states of the lattice, which are highly non-classical states. And we have all these data points, and of course we can support them by direct numerical diagonalization of the Hamiltonian, which you can see fit quite well here. And now let me bisect this diagram into two, exactly on the line where both orthogonalization times are equal. So with respect to that line, we have the two dynamical regime. Thanks. So at the left side, we have the Margalus-Levitin regime, where at some point we have a crossover to the energy-dependent type of dynamics, where to the right of this line, we have the empty regime, where the energy uncertainty dictates the dynamics throughout time, throughout the evolution, basically. This can be compared to two analytic cases. So the qubit, we see it fits our data for very small excitation, where we have mainly the ground state and some small hybridization of the first excited state. And if we want to go further than that, we can compare our evolution to the Poissonian state. So this is a coherent, the Poissonian distribution of a coherent state, and we can see it approximates our dynamic quite well, but then it diverges quite significantly from it. Namely, we get far from this semi-classical regime, or due to the non-harmonicity of the potential. So this is how we diverge from it. So with that, I'd like to conclude. So basically, we probed both quantum speed limits in a multi-level system, and by probing the two limits, we saw this crossover in time between them, or between the two types of evolutions. I did not have time to go into that, but also when we try to quantify the distance from the bound, how much the evolution is slower than the bound itself, we found unexpectedly a universal small deviation from the bound, and this hints for a very useful character of the bound, that you can actually use the energy uncertainty to assess the rate of evolution in the system, kind of circumventing the need for full state homography. So it's very, like this bound have some applicative feature. And of course, the next steps would be to take a look at open systems where the theoretical grounds are less firm. So I invite you to find out more in our publication from last Wednesday, and you can use this QR code. And I'd like to thank my team. So I'm from Yoav Sagi's group at the Technion, and this work was done in collaboration and in the lab of Dieter Meschede. Especially I'd like to acknowledge Andrea Alberti, the PI, and Manolo Rivera Lam, who worked with me on this project. And thank you for your attention.